We live in a world that is just, absolutely swimming in digital data, binary code, gigabytes, instant uploads. It's everywhere.
Hmm.
But when you actually step back, you realize all the exciting, palpable action we care about, sound waves, temperature changes, light, physical motion, it's all fundamentally analog.
Right. It's continuous, it's messy, it's infinitely variable.
Exactly.
And the entire foundation of modern engineering, from IoT to industrial control, is really just dedicated to building a robust bridge between those two, well, incompatible universes.
And that bridge is conversion,
Yeah.
analog to digital, or ADC, for reading the real world.
And digital to analog DAC for controlling it.
So today we are taking a deep dive into the engineering compromises and, frankly, the technical pitfalls that happen right at that crucial intersection.
Yeah?
We've synthesized some pretty serious technical reports from giants like Texas Instruments and Zilog, practical guides from experts at Ursa and DigiKey, and we've even pulled in some lively community debates about microtiming precision.
And our mission here is to move way beyond just the simple definitions. We are here to unpack the critical specifications, the complex trade-offs that, if you ignore them, can make conversion what did one source call it?
A chancy thing.
A chancy thing, exactly.
Sure.
We want to make sure you understand when you can safely rely on simple, built-in components like, say, the 10-bit converter inside an Arduino, and when the application absolutely demands, you go for external, high-precision hardware.
Okay, let's unpack this starting at the most basic level. If you look at any microcontroller, you see pins labeled analog and digital. What's the fundamental practical difference?
Well, the core difference is continuity versus quantization.
Right.
Analog I/O is continuous.
Okay.
Theoretically, it can take on any voltage value within its range, from 0 volts up to 5 or even 20 volts. It measures the input continuously.
So like a water level sensor in a tank, it doesn't just say full or empty.
Exactly. It returns a specific voltage, 3.2 volts, 3.201, 3.209 dash. That corresponds precisely to a specific water height. It gives you the gradation.
But how much?
Precisely. Digital I/O, on the other hand, is purely binary. It's just HEH or low W. On or off. 1 or 0.
Simple.
Much simpler, faster, and cheaper to implement because you just need to check a single threshold. In your water tank system, digital would be for the simple stuff, like turning a valve on or off F.
And you see that reflected in the hardware. Most microcontrollers have way more digital pins, maybe 14 or more, than they do analog inputs, which might just be 6 or 8.
Because those analog pins require specialized hardware to deal with that messy, continuous world. And they often default to a standard 10 bits of resolution.
Which is often enough.
Until it isn't.
Which brings us directly to our next point. So let's say I'm building a high-fidelity sensor system and I pick a 12-bit ADC chip. That sounds great, right? Over 4,000 possible values. But our sources suggest that just relying on that single bit number is a recipe for disaster.
Yeah.
Why is specifying a converter so deceptive?
Because we have to very clearly distinguish between resolution and accuracy.
Okay.
Resolution is, it's a design parameter. If you have an n-bit converter, it mathematically resolves one part in 2 to the n. A 12-bit ADC can theoretically resolve one part in 4,096.
Which is tiny, like 0.02% of the full scale.
Extremely fine, yes. And that smallest measurable increment, that is the definition of one least significant bit 1 LSB.
So resolution is the potential sharpness of the picture, but why is the real-world accuracy always lower?
Because accuracy is the reality check. It describes the worst-case deviation from the ideal straight line, and it has to include all the real-world errors.
Like what?
Thermal drift, manufacturing tolerances, offset errors, gain errors, everything. And what's more, just because of the math of it all, even a theoretically perfect 12-bit ADC can't have an accuracy better than plus or minus half an LSB.
Right, and that's the inherent quantizing error. It's unavoidable. You're taking a smooth, continuous signal, and you're forcing it into discrete, finite digital steps.
Exactly. The analog input might fall anywhere between the threshold for, say, code 10 and code 11, but the converter has to choose one.
It has to round up or down.
And that tiny difference between the true analog value and the digital code it assigns, that is the quantizing error. It's just the price you pay for digitization.
Okay, that makes sense. But beyond just accuracy, the reports really hammer on specifications like linearity and monotonicity, especially for control feedback systems. Why are those so crucial?
They define system stability. Linearity, specifically integral nonlinearity or INL, describes how far the ADC's actual performance departs from that perfect mathematical straight line after you fix the basic offset and gain errors. But the real system killer is monotonicity.
All right, this is where it gets really interesting. What happens if a converter is non-monotonic?
A monotonic curve has to have a positive or zero slope only. The output value must never, ever decrease when the input command increases. A non-monotonic curve has steps that actually go backward.
And the sources call that
A disaster in closed-loop servo systems. That's a direct quote.
Give us an example of that disaster. What does that look like?
Okay, imagine you're telling a precise robotic arm to slightly slow down a motion. So you send a command to the DD to lower the output voltage by one tiny step 1 LSB.
A very small change.
A tiny change. But if the DD is non-monotonic, the actual voltage might temporarily jump up by 2 or 3 LSBs before it corrects itself.
Whoa.
So the control system, which was expecting a small decrease, suddenly sees a large reversal and it instantly overcorrects. This leads to oscillations, instability, chatter. It can physically damage the system.
So how do you avoid that?
The good news is, if you can keep your total linearity error, both INL and DNL, within plus or minus half an LSB, you are mathematically guaranteed to have a monotonic system. It's the key metric for stable control.
That is the essential insight. It's not just about the number of bits, it's about the quality control of those bits.
Absolutely. Beware of the specs indeed.
So let's pivot to the practical decision. When do I scrap the ADC that's built into my microcontroller, the one that comes for free, and buy a specialized external one?
If your application is pretty moderate, so sampling rates under, say, 200,000 samples per second, and you need maybe 10 or 12 bits of effective resolution, the internal ADC is usually fine. It's cheap, it's simple to integrate.
But the moment you cross that boundary, you have to go external. What are the non-negotiable thresholds?
You have to switch if you hit thresholds in speed, accuracy, or features.
Okay, let's take those one by one. Speed.
Speed is easy. If you need sampling rates over 1 million samples per second, or you need multi-channel high throughput, internal ADCs just won't keep up.
And accuracy.
If you need an effective resolution, the true effective number of bits, or ENOB, that's greater than 12 bits, or if you need guaranteed super tight linearity specs that internal chips just don't deliver consistently, you have to go external.
And that third category, features, includes something called simultaneous sampling. Why is that one so critical it demands an external chip?
Okay, so for demanding systems like a three-phase motor control, you have to measure the current and voltage on multiple channels at the exact same instant. Internal ADCs usually use a single conversion unit that just switches between different input pins, a multiplexer. This introduces a tiny but absolutely critical time skew between the measurements.
So if I measure phase A and then phase B a microsecond later, the data is already useless for calculating the current motor position.
Completely useless. That time skew introduces a phase error, which totally messes up the electrical angle estimation you need to smoothly control the motor.
And an external ADC solves this how?
Dedicated external ADCs often have per-channel sample and hold circuits. They grab all the readings at the identical clock edge. No skew.
Now, what about the engineering hack? I've heard you could just oversample and average the internal ADC readings. If I average 16 readings, I've gained 2 bits, right?
It's actually the square root of n, so you'd improve by a factor of 4, which is equivalent to 2 bits, yes. And averaging 256 readings would get you another 2 bits.
So why isn't that a true replacement for better hardware?
That is the most common misconception. Oversampling and averaging definitely help. They reduce random noise, they stabilize the readouts, they make your readings look much, much smoother.
But I'm still stuck with the hardware's limitations.
You are. The key thing is that averaging does not fundamentally raise the true effective number of bits. ENOB is limited by the hardware's own built-in linearity and its thermal noise floor.
So if the hardware is nonlinear?
Averaging just gives you a very precise average of those systemic nonlinear errors. You cannot filter out poor hardware design with better software. If you truly need 14 or 16 bits of effective precision, you must use external hardware.
That's a critical distinction. Oversampling makes the noise look prettier, but the actual integrity of the data hasn't fundamentally improved.
The output is smoother, but the accuracy is only marginally better.
Let's flip the conversion. What if I have a digital system that needs to create a smooth analog output, say dimming an LED, but my microcontroller is a cheap one without a dedicated DAC?
This is where the ingenious pulse width modulation, or PWM, comes in as a low-cost DAC substitute.
The PWM hack.
Exactly. PWM generates a digital signal at a constant frequency. The analog value you want is just represented by the duty cycle, the fraction of time the signal is held, HIGH.
So if my supply voltage is 5 volts and I set the duty cycle to 50%, the average output voltage is 2.5 volts.
That's your analog equivalent. But and this is critical, that output is still a square wave, a choppy digital signal. To turn it into a smooth, usable analog voltage, you have to filter it.
Usually with a simple RC low-pass filter to start.
Right, to demodulate the signal and get the average DC value.
And this is where we run straight into that classic embedded design trade-off. Accuracy versus speed, or ripple versus bandwidth. How does that play out here?
The relationship is inverse and, well, it's painful. If you increase the PWM resolution, meaning you use more clock pulses to get finer steps, you automatically lower the PWM carrier frequency.
And a lower frequency is harder for the filter to remove.
It's much harder. It dramatically increases the demodulation ripple voltage for a given filter. So if you need low ripple-high analog accuracy, you are forced to use a much slower filter, which in turn kills your system's bandwidth.
So you trade responsiveness for purity.
That's it. You can have a high-resolution output, but your motor speed or your light dimmer will react very sluggishly.
And if that simple RC filter isn't good enough,
Then you move to more complex active filters. And the choice depends entirely on what you're trying to preserve. A Butterworth filter, for example, gives you a maximally flat passband, zero distortion for the frequencies you care about.
but it's slow.
It can introduce significant phase delay, yes. If you need to react faster, you might look at a Chebyshev filter, gives you a much sharper cutoff, but the cost is you have to accept some gain ripple in your signal.
Okay, but our sources mention one filter as being particularly good for PWM, the Bessel filter. Why that one?
Because the Bessel filter is designed for linear phase response. It ensures that the time delay across all the relevant frequencies is constant.
Ah, so it preserves the timing.
Exactly. This is crucial for preserving the integrity of that pulse train as it's being smoothed out. It's extremely well suited for demodulating PWM without adding unwanted distortion or time skew to the output.
Shifting gears now from the hardware to the software timing that manages all of this. How does a microcontroller decide when to handle these events? This is that core debate between interrupts and polling.
Right, and this is a fundamental trade-off between responsiveness and determinism. Interrupts, or ISRs, are essential for real-time, time-critical events.
Like a sensor hitting a danger threshold.
Exactly. Or a communication line receiving a character. They immediately suspend whatever the main program is doing.
And the cardinal rule for interrupts, which every guide stresses, is they have to be efficient.
They must be lightning fast and concise. Their job is to handle the immediate flags, set a state variable, maybe grab a piece of data, and get out. They have to defer any heavy processing to the main loop.
Why is that deferral so crucial?
To prevent things like stack overflow. But more importantly, to prevent the disruption of critical timing. If your main program needs to send out a pulse that is exactly 50 microseconds wide,
You can't have a long-running interrupt jump in and stretch it out to 60.
you can't. That would violate the protocol. Determinism is key.
So if interrupts are so great for immediate response, when would a developer ever choose polling, where the CPU just constantly checks the status?
Polling is favored when you need the program to be completely deterministic, especially during those critical timing windows. It also simplifies the firmware by avoiding concurrency issues like race conditions. But maybe the most counterintuitive reason is when the event frequency is just too high.
Wait, polling is faster than interrupts at high frequency.
It can be. If an event is firing, say, 30,000 times a second, the total overhead of the interrupt context, switch saving the CPU state, jumping to the ISR, executing, restoring the state, it becomes prohibitively costly.
I see.
A tight, well-written polling loop can sometimes process that event faster because it avoids all that context switching.
So the interrupt is great for low-frequency, urgent events, but high-frequency events penalize you for the switching time.
And finally, there's the massive power implication. With interrupts, the MCU can go into a deep sleep mode and only wake up when an event occurs. This saves tremendous power for battery devices.
While polling,
Polling requires the CPU to stay constantly active, continuously reading memory. It's what one user called hitting the bus hard, and it just wastes energy.
this deep dive has really exposed the layers of complexity here. We started with what seemed like a simple translation problem, and we ended up facing this cascading set of trade-offs.
Absolutely. Hardware, software, timing, power. Every specification is interconnected. The number of bits you choose affects your linearity, which dictates if you need external hardware.
That choice then impacts your data rate, which determines your filter design.
Which then determines your software architecture. It's a chain of compromises. The precision of your entire system is only as good as the weakest link in that conversion chain.
So, As you look at your next engineering design, or even if you're just evaluating the quality of your favorite audio device, now that you understand the crucial difference between theoretical resolution and real-world effective resolution.
Consider which component of that system is currently relying on a poorly tuned internal ADC, maybe covered up with some simple averaging, and is therefore creating more noise than actual reliable knowledge. Understanding that effective resolution is the true measure of performance. That's what dictates the final quality of everything you build.